Thank you. This is 600, also known as Introduction to Computer Science and Programming. My name is Eric Grimson. Together with Professor John Guttag over here, we're going to be lecturing the course this term. I want to give you a heads up. You're getting some serious firepower this story. The second thing we want to do is we want to help students who don't plan to major in Course 6 to feel justifiably confident in their ability to write and read small pieces of code. For all students, what we want to do is we want to give you an understanding of the role computation can and cannot play in tackling technical problems, so that you will come away with a sense of what you can do, what you can't do, and what kinds of things you should use to tackle complex problems. And finally, we want to position all students so that you can easily, if you like, compete for things like UROPs and summer jobs, because you'll have an appropriate level of confidence and competence in your ability to do computational problem solving. Those are the strategic goals. Now, this course is primarily aimed at students who have little or no prior programming experience. As a consequence, we believe that no student here is underqualified for this. Okay, those are the top-level goals of the course. Let's talk sort of at a more tactical level about what do we want you to know in this course. What do we want you to be able to do by the time you leave this course? So here are the skills that we would like you to acquire. All right, the first skill we want you to acquire is we want you to be able to use the basic tools of computational thinking to write small-scale programs. We're going to keep coming back to that idea, but I'm going to call it computational thinking. And that's so you can write small pieces of code. And small is not derogatory here, by the way. It just says the size of things you're going to be able to do. Second skill we want you to have at the end of this course is the ability to use a vocabulary of computational tools in order to be able to understand programs written by others. So you're going to be able to write, you're going to be able to read. This latter skill, by the way, is incredibly valuable, because you don't want to do everything from scratch yourself. You want to be able to look at what is being created by somebody else and understand what is inside of there, whether it works correctly, and how you can build on it. This is one of the few places where plagiarism is an okay thing. It's not bad to, if you like, learn from the skills of others in order to create something you want to write. Although we'll come back to plagiarism as a bad thing later on. Third thing we want you to do is to understand the fundamental both capabilities and limitations of computation and the costs associated with them. And that latter statement sounds funny. You don't think of computation having limits, but they do. There are some things that cannot be computed. We want you to understand where those limits are. So you're going to be able to understand abilities and limits. And then finally, the last tactical skill that you're going to get out of this course is you're going to have the ability to map scientific problems into a computational framework. So you're going to be able to take a description of a problem and map it into something computational. Now, if you think about it, boy, it sounds like grammar school. We're going to teach you to read. We're going to teach you to write. We're going to teach you to understand what you can and cannot do. And most importantly, we're going to try and give you the start of an ability to take a description of a problem from some other domain and figure out how to map it into that domain of computation so you can do the reading and writing that you want to do. Okay, in a few minutes, we're going to start talking then about what is computation, how are we going to start building those tools, but that's what you should take away. That's what you're going to gain out of this course by the time you're done. Through working on problem sets, and all the problem sets are going to involve programming in Python, which is the language we're going to be using this term. Now, one of the things you're going to see is the first problem sets are pretty easy. Actually, that's probably wrong, John, right? They're very easy. And we're going to ramp up. By the time we get to the end of the term, you're going to be dealing with some fairly complex things. So one of the things you're going to see is we're going to make heavy use of libraries or code written by others. It'll allow you to tackle interesting problems without having to write from scratch. But it does mean that this skill here is going to be really valuable. You need to be able to read that code and understand it, as well as write your own, so that we can deal with that. Okay, the quizzes are open book. This course I want you to take your own notes to help you, if you like, spur your own learning process. All right, and then finally, the course is not about memory. It's not how well you can memorize facts. In fact, I think both John and I are a little sensitive to memory tests given our age, right, John? This is not about how you memorize things, it's about how you think. So they're open note, open book, and it's really going to test your ability to think. The problems are set up so that if you start down the right path, it should be pretty straightforward to work it through. If you start down a plausible but incorrect path, you can sometimes find yourself stuck in the weeds somewhere, and we want to bring you back in. So part of the goal here is this should not be an grueling, exhausting kind of test. It's really something that should be helping you learn the material. Let's talk about computation. As I said, our strategic goal, our tactical goals are to help you think like a computer scientist. Another way of saying it is we want to give you the skills so that you can make the computer do what you want it to do. And we hope that at the end of the class, every time you're confronted with some technical problem, one of your first instincts is going to be, how do I write a piece of code that's going to help me solve that? So we want to help you think like a computer scientist. All right? And that is an interesting statement. What does it mean to think like a computer scientist? Well, let's see. Primary knowledge you're going to take away from this course is this notion of computational problem solving, this ability to think in computational modes of thought. And unlike in a lot of introductory courses, as a consequence, having the ability to memorize is not going to help you. It's really learning those notions of the tools that you want to use. But what in the world does it mean to say computational mode of thought? It sounds like a phrase you use when you're trying to persuade a VC to fund you. Right? So to answer this, we really have to ask a different question, or related question. So what's computation? Sounds like a strange statement, right? What is computation? And part of the reason for putting it up is that I wanted, as much as possible, answer that question by separating out the mechanism, which is the computer, from computational thinking. Right? The artifact should not be what's driving this. It should be the notion of what does it mean to do computation? Now, to answer that, I'm going to back up one more level. And I'm going to pose what sounds like a philosophy question, which is, what is knowledge? And you'll see in about 2 minutes why I'm going to do this. But I'm going to suggest that I can divide knowledge into at least 2 categories. Okay, what is knowledge? And the 2 categories I'm going to divide them into are declarative and imperative knowledge. All right, what in the world is declarative knowledge? Think of it as statements of fact. It's assertions of truth. Boy, in this season, that's a really dangerous phrase to use, right? But it's a statement of fact. I'll stay away from the political comments. Let me give you an example of this, right? Here's a declarative statement. Square root of x is that y such that y squared equals x, y is positive. You all know that. But what I want you to see here is that's a statement of fact. It's a definition. It's an axiom. It doesn't help you find square roots. If I say x is 2, I want to know what's the square root of 2. Well, if you're enough of a geek, you'll say 1.41529 or whatever the heck it is. But in general, this doesn't help you find the square root. The closest it does is it would let you test. You know, if you want to test something, but it doesn't tell you how to. And that's what imperative knowledge is. Imperative knowledge is a description of how to deduce something. So let me give you an example of a piece of imperative knowledge. All right, this is actually a very old piece of imperative knowledge for computing square roots. It's attributed to Heron of Alexandria. Expected of knowing it beforehand. But here is a piece of imperative knowledge. All right? I'm going to start with a guess. I'm going to call it G. And then I'm going to say, if G squared is close to X, stop. And return G. It's a good enough answer. Otherwise, I'm going to get a new guess by taking G, X over G, adding them, dividing by 2. I'm going to take the average of G and X over G. Don't worry about how it came about. Heron found this out. But that gives me a new guess. And then I'm going to repeat. That's a recipe. That's a description of a set of steps. And notice what it has. It has a bunch of nice things that we want to use, right? It's a sequence of specific instructions